Assignment number 4, problems 19, 20, and 25 on page 65.
Problem 19. A bus that is traveling at 30 kilometers per hour speeds up at a constant rate of 3.5 meters per second squared. What velocity does the bus reach 6.8 seconds later? The initial, the final, A, T, D. The initial is 30 kilometers per hour. The final is what we're trying to find. Acceleration is 3.5 meters per second squared. It's speeding up, so A is a positive number. Time is 6.8 seconds, and displacement is what's missing. V final equals V initial plus A T. V initial is 30 kilometers per hour. A is 3.5 meters per second squared. Time is 6.8 seconds. So V final is 30 kilometers per hour plus 23.8 meters per second. But kilometers per hour, meters per second don't match. So since buses are normally measured in kilometers per hour, we'll convert the 23.8 to kilometers per hour. And to do that, we multiply by 1 kilometer over 1,000 meters, and then multiply by 3,600 seconds over 1 hour. And when we do that, we get 30 kilometers per hour plus 85.7 kilometers per hour. So V final equals 115.7 kilometers per hour. Final velocity of the bus is 115.7 kilometers per hour. Problem number 20. If a car accelerates from rest at a constant 5.5 meters per second squared, how long will it take for the car to reach a velocity of 28 meters per second? So again, we list our variables to see what's known and not known. Accelerates from rest, so V initial is 0. Tell us acceleration is 5.5 meters per second squared. How long will it take times what we're trying to find to reach a velocity of 28 meters per second is V final, and distance is missing, so we use the equation V final equals V initial plus AT, which we can rearrange to T equals V final minus V initial over A. So that gives us 28 meters per second minus 0 meters per second divided by 5.5 meters per second squared. T equals 5.1 seconds.
Problem number 25 is what I call the running out of gas problem. Now, the version of this problem in the current edition of the textbook is different from that in the previous edition of the textbook. The following PowerPoint presentation was created using the version in the previous edition. This is what I call the running out of gas problem, which is problem number 25 in the current version of the textbook, but was problem number 16 in a previous version, and that is the version on which this PowerPoint was based. Okay, the car is driven at a constant velocity of 25 meters per second for 10 minutes. The car runs out of gas, so the driver walks in the same direction that he had been driving in at 1.5 meters per second for 20 minutes to get to the nearest gas station. After spending 10 minutes filling a gasoline can, the driver then walks back to his car at a slower speed of 1.2 meters per second. The car is then driven home at 25 meters per second in the direction opposite to that of the original trip. Part A. Draw a velocity time graph for the driver using seconds as your time unit. Note, you will have to calculate the distance that the driver walked to the gas station in order to find the time it took the driver to walk back to the car. So, let's get started. So at the beginning of the problem, the car is going at a constant velocity of 25 meters per second. So, in a velocity time graph, constant velocity is represented by a horizontal line. How long do we make this horizontal line? Well, the motion was going on for 10 minutes, but they want the unit in seconds, so 10 minutes is 600 seconds. So the first segment of the graph is a horizontal line as shown on the graph. Then what happens? He runs out of gas, so the driver walks in that same direction at 1.5 meters per second. Again, we have to assume it's a constant speed, so we need another horizontal line. And how long is 20 minutes? That would be 1200 seconds. So there's 1.5, but 1200 seconds starting at time equals 600 seconds. So by the time he arrives at the gas station, the total time that has passed is 1800 seconds. So that's the second part of his journey. What's happening at the gas station? Well, he remains there for 10 minutes. Well, that means his velocity is 0. 10 minutes, again, is 600 seconds, so we add another 600 seconds to the 1800 seconds, and that brings us to 2400 seconds, so here's the third segment of his journey. Now the driver walks back to his car, but they tell us he's going slower. He's now walking at 1.2 meters per second. Why is he walking slower? Well, probably because he's carrying the heavy can filled with gasoline. One thing to note, if he's going back in the opposite direction, back to his car, the velocity is actually negative 1.2 meters per second, which we put there below the x-axis, but for how long? They didn't tell us how long it took him to walk. Well, since he's going slower than he was originally, it took him 1200 seconds to walk to the gas station. If walking back to his car is going at a slower pace, you can reasonably assume it's going to take longer than 1200 seconds. But exactly how long? Well, how far away was the car from the gas station? Well, d equals vt. Since he was going at a constant speed, he was going at 1.5 meters per second times 1200 seconds. We don't have to actually solve for d because on the way back, vt is the same distance. Whatever distance he walked to the gas station, he had to walk the same distance back to his car. So we can set up the equation 1.5 meters per second times 1200 seconds equals 1.2 meters per second times t. And when we solve for t, we find it took him 1500 seconds to walk back to his car. So 1500 seconds added to the 2400 seconds that's already elapsed, and we find that it is time equals 3900 seconds by the time he gets back to his car. Notice this line is below the x-axis because, as we said, he's now walking in the opposite direction, so it's a negative velocity. So now he drives back home at 25 meters per second, negative again because he's going in the opposite direction. Well, if it took him 600 seconds to get from his home to the gas station, it's going to take him 600 seconds to get from the gas station back to his home. So adding 600 to the 3900 gives us 4500 seconds, and that's the final segment of his journey. Part B asks us to draw a position time graph for this problem. And in order to do so, we have to use the areas under the curve of the velocity time graph to calculate the positions at various times. This first rectangle represents the distance covered by the car during the first 600 seconds, so it would be 25 meters per second times 600 seconds gives us 15,000 meters. Similarly, the second rectangle is calculated to be 1,800 meters. The next segment, well, that's when he's stationary, so he's not moving at all, so his change in position is 0 meters. Moving along, the next rectangle is negative 1,800 meters, and the final rectangle is negative 15,000 meters. Why are they negative? Well, notice they are below the x-axis. In these two cases, his displacement is back towards where he started from, back towards his house, or the opposite direction of the first two rectangles. Now we need to make a table of time versus displacement. At the end of 600 seconds, the driver's displacement was 15,000 meters. At the end of 1,800 seconds, he went an additional 1,800 for a total of 16,800 meters away from his home. Now, during the time he was at the gas station, his displacement did not change, so at the end of 2,400 seconds, his total displacement is still 16,800 meters away from his home. Now he starts walking back towards his car, and his displacement for the next segment is negative 1,800 meters, so at the end of 3,900 seconds, he is once again 15,000 meters away from his home. And finally, for the last segment, his displacement is negative 15,000 meters, so that at the end of 4,500 seconds, the person is now at 0 displacement, that is, he is back home again. Now we use this data to construct a position time graph. As you can see from the graph, I've already put in the key values on both the x and the y axes. Now, it's not listed on the data table, but if you think about it, at time 0, where was the guy? At time 0, he was at home. So 0 displacement. So even though it's not on the table, 0, 0 is in fact a data point. Then the next data point would be 600, 15,000. So we draw a line connecting these two data points, and it should be a straight line. Why is it a straight line? Because when you think about it, the guy was driving at constant speed, and the slope of the displacement time graph is the speed or velocity. Next data point is 1,800, 16,800, and that's the second segment to connect the second and third data points. At time equals 2,400 seconds, he is still at position or displacement 16,800, so the next segment is a horizontal line. And what does a horizontal line mean? It means the speed or velocity is 0. That makes sense. He's stationary at the gas station, so yes, his speed is 0 for that time interval. Now he starts walking back towards his car, so at time equals 3,900 seconds, his displacement is once again 15,000 meters. So when we draw in that segment, it has a negative slope because he's walking in the opposite direction. And finally, at time is 4,500 seconds, he's back home, or 0 displacement. And so there's the final segment, and this is what the completed graph looks like. Now, if we were to calculate the slopes of each of these segments, we would find that they do in fact correspond to the velocity of the person at each of these time intervals. So, the take-home lesson from this problem is that given a verbal description of an object's motion, you should be able to generate both a position time graph and a velocity time graph. And given either graph of an object's motion, you should be able to verbally describe the motion of that object.